This is physics paper 4, theory extended from 0625. That is stroke 412. There is a February March 2023 paper, the paper that was done this year. So let's go through this paper. Now, question number 1, part A. A boat crosses a river. The boat points at right angles to the riverbank, and it travels at a speed of 3.5 meters per second relative to the water. A river current acts at right angle to the direction of the boat points. The river current has a speed of 2.5 meters per second. By drawing a scale diagram or by calculation, determine the speed and the direction of the boat relative to the riverbank. This question is very direct, at least it's easy because you have been given, like two options. You can do by scale diagram or by calculation. By scale diagram, I've done a video of explaining the vector resolution. So if you get some chance, please also look for that video, or you can able to see the link above here. By calculation is very easy. If we consider this to be the river bank, so the boat is here, which tends to move perpendicular to the river bank. Then if we take this to be the direction in which the water of the river is flowing. So for that matter, we will able to have, so this is the direction of the flow of the river. Then we take this to be the direction of the boat crossing the other side. Then you can able to see clearly that the resultant velocity will be along this, which is the hypotenuse. So this is 3.5 meters per second, and then there is 2.5 meters per second. So with this, to find this particular part here, that is, we'll use this. C squared is equal to A squared plus B squared. That means our C here is the speed we're looking for. So B will be equal to 3.5 squared plus 2.5 squared. Then we find the square root. That gives us 4.301. So into, 4.3. That is 4.301. So into two significant figures, that will be 4.3 meters per second. The direction relative to the river bank, that means we look for the angle. So from this diagram here, you can able to see the river bank is along this particular part. That means we are looking for this angle here, this angle theta. That is what will give us the direction along or relative to the river bank. But you can able to find this angle, which I can call alpha. So this angle is adjacent to 3.5, but opposite 2.5, meaning I can use tan here. So tan alpha is given by opposite 2.5 over adjacent, which is 3.5. So gives us 35.5 degrees, meaning that theta, which we're looking for, is 90 minus 35.5. And that is 54.5. 54.5 degrees. That is the direction relative to the riverbank. Now, speed is a scalar quantity and velocity is a vector quantity. State the names of one other scalar quantity and one other vector quantity. So for this question here, we are going to name all the scalar quantities and any of the scalar quantity and any of the vector quantity, but you cannot include speed and velocity because you've been given already as examples. So for the speed, for the scalar, we talk about distance, mass. So think of all the scalar quantities: time, energy, temperature, Of course, we know we have speed here, but speed is already mentioned here. Vector quantities, we have velocity, it has been mentioned, displacement, we have momentum, let me call it P, we have weight, let me call it W, we have force, but please, in the exam, write them in full, so please, let me just write them in full. So displacement, weight, momentum, we're just supposed to mention one, ETC, electric field strength, all those are vector quantities. The figure 2.1 shows a ship loaded with containers. The ship is made of steel. The density of steel is 7,800 kilogram per cubic meters, and the density of water is 1,000 kilogram meters per cubic meter. Sorry. So explain why the ship floats in the water. So one obvious thing is that for something to float on, in a fluid, it means it's less dense than that fluid. So, but then we're asking ourselves, is steel, the density of steel is 7,800. How is it less dense than water? So this makes us, we need to reason out here. We know that the ship is not like a complete, like a solid steel throughout, but it's made of air. That means there's a mixture of air and steel, and therefore the average density of the ship is less than the density of water, and that is why it floats. Huh? That is very obvious. So we can make here that the ship is not, or we can say that the ship is made of the steel and also air. What does it mean? This means that now the average density of the ship is less than the density of water, and that is why now the ship floats. But now, if we look at the advanced part of it, we can able to apply the Archimedes principle. We said that for the ship to float, it means it depends on the amount of water that has been displaced. So the amount of water displaced here is equal to the upthrust, experienced by the ship. So that is also another way that can be considered. So, but the containers with the greatest mass are loaded near the bottom of the ship, and explain the effect on the stability of the ship of loading the containers this way. So if containers are loaded at the bottom, what is the effect of this? The effect of this is that what? It lowers the center of gravity of the ship. And by lowering the center of gravity, this increases the stability of the ship. So low center of gravity increases or makes the ship to be more stable. But see, a crane lifts a container 48 meters vertically upwards. The mass of the container is 30,000 kilograms. Calculate the energy transferred to the gravitational potential energy stored in the container. So this is just formula. So GPE, or gain GPE, is given by mgh. So the mass is 30,000. G is 9.8 as provided by this. And then H is 48. So this is just direct calculation. So that is 30,000 times 9.8 times 48. That gives us 14. And say 1.4 times 10 power 7 joules of energy. State the principle of conservation of energy. Now, principle of conservation of energy states that energy cannot be created. Energy cannot be created or destroyed. If you mention that, that will only give you 1 mark. So we have to complete that side by saying, but can only be transformed or transferred from one form to another, but can only be transferred from one form to another, or from one energy store to another. So from one energy store to another, or from one form to another. Part B, a wind turbine has a maximum output power of 1.8 megawatts. The turbine operates at a maximum power for 4.0 hours. Define the unit kilowatts hour. Kilowatts hour is the energy transferred. So this is the energy transferred in 1 hour. In 1 hour at the rate of 1 kilowatts. At the rate of 1 kilowatt. So Roman 2, calculate the energy produced by the wind turbine operating at maximum power for 4.0 hours. Give your answer in kilowatts hours. So we know that very well that energy transferred during this period is given by power times time. So the power is given as 1.8 megawatts. So 1.8 mega is 10 power 6 watts times time. Time is 4 hours. We will not change to seconds because we have been told to give our answer in kilowatts hour. That means we have 4.0. So we now have, you get 7.2. That will be 7.2 times 10 power 6 watts hour. But now we have to add this kilo. Kilo is a prefix, which is 10 power 3. That means we divide this by 1,000. Because 1,000 is 1 kilowatt, 1 kilo. So dividing by 3, that will be 7,200 kilowatts hour, because K here is 1,000. Okay. Radiation from the sun is the main source of energy for most of our energy resources. State 2 energy resources that are not due to radiation from the sun. If you look at this, geothermal is not due to the radiation from the sun. We are talking about tidal, which is tidal energy is due to the gravitational moon's gravity. Then we look at nuclear energy from the nuclear reactions. That is also not from the. So two of them will give you the full answer. Number 4, figure 4.1 shows a metal pan on an electric hot plate. The pan contains 200 cubic centimeter of water. So we have the diagram there. The pan is heated. The temperature of the water in the pan increases. The thermal energy is transferred through the metal pan by conduction. That's correct. State and explain 2 ways that thermal energy is conducted in metal. Now, these are mechanisms in which energy is being transferred. So we know very well that what metals have free electrons. So metals have free electrons. Metals have free electrons, and also conduction occurs by vibration of the lattice, or that is vibration of the atom. So metals conduct heat by free electrons, by the flow of free electrons, and also the vibration. So we can say here that metals have free or mobile electrons. So what do they do? So when electrons are transferring energy, they collide. So the electrons move and collide with the atoms, thereby transferring energy to them. So therefore, the molecules or the atoms, or the molecules in the lattice so metals have free electrons. So these electrons move and collide with the atoms, thereby making the electrons, the molecules to vibrate. So as they vibrate to those that are next to them, and therefore ensuring the transferring of energy from one particular point to another. Part B, Roman 1. Water boils and leaves the liquid as a gas. Explain in terms of force and distance between the particles why the gas occupies much greater volume than it does as liquid. So this is about in terms of force and distance. So we know very well that for gases, the intermolecular forces of attraction, of gases is weak compared to those of the liquid. And if you talk about the distance, so you can talk about the intermolecular distance. So the distance between the molecules of a gas or gases is bigger compared to those of the liquid, and therefore they occupy a greater force, a greater space. State 2 ways in which boiling differs from evaporation. So boiling occurs at fixed temperature, while evaporation occurs at all temperature. Boiling occurs throughout the liquid. It occurs throughout the part of the liquid, while evaporation occurs at the surface of that liquid. Boiling does not cause cooling effect, while evaporation causes the cooling effect. The water is replaced with 200 cubic centimeter of milk. The initial temperature of the milk is 20.0 degrees Celsius. The boiling point of the milk is 95.0 degrees Celsius. The milk starts to boil when 60,700 joules of thermal energy has been transferred to it. The density of the milk is 1.03 grams per cubic centimeter. Calculate the value of the specific heat capacity of milk. Give your answer into 3 significant figures. So we know that specific heat capacity is the energy transferred per unit mass and per unit change in temperature. So this energy transferred there is 60,700 joules over mass. Let's see the unit. Oh, this is, we can give our answer in terms of grams or in terms of kilograms. So let's see. We have the volume and we have the mass, the density. Therefore, mass is density times volume. That is 1.03 times 200, 206 that is 206 grams, which is equivalent to 0.206 kilograms. If I use 206 grams, then this will be that's how we put our answer, 200 grams times change in temperature, that is from 20 to 95. The change in temperature will be 75. So the answer will be 3.93 joules per grams per degree Celsius. Or in other words, you can just say like this, per, then you put a bracket like this, so that you remove per. So grams per degree Celsius. Or if it is in kilogram, we will have 6,700 joules over 0.206 times 75. This will give us 3,930 joules per kilogram per degree Celsius. That is if it is in kilogram. So this question is open. The unit is open, so it's you to determine. So as long as you get the correct unit, you're able to score. So if you don't convert this into kilogram, then remember that this will be in grams. If you convert to kilogram, then this part here, the unit will be joules per kilogram per degree Celsius. So either is correct. But please be warned, there are some questions where they give you the unit here. So you must convert your working or the input into the units that is being provided. Number 5, part A, figure 5.1 shows a semicircular transparent plastic block. A ray of light is incident normally on the curved surface of the block. The refractive index of the plastic is 1.5. Calculate the critical angle for this plastic. So this one here is direct. So we know that refractive index is given by 1 over sine C, where C is the critical angle. That tells you that sine C is equal to 1 over 1.5. So to find C, we will find the sine inverse of 1 over 1.5. That will give us 41.8. So that is 41.8 degrees. 41.8.
So on the figure 5.1, draw the path of the ray in the block, and after the ray emerges from the glass block. Now, for us to know how the ray of light is going, whether it's going to be refracted or is going to undergo total internal reflection, then we need to extend this ray of light up to here, then measure the angle of incidence. When angle of incidence is less than the critical angle, for our case is 42 degrees, then the ray of light will be refracted into the air this side. But if the angle of incidence is greater than the critical angle, which is 42 degrees, then it will undergo total internal reflection. So let's find out. So the first thing is to extend the ray of light. And you can see clearly this angle, this is 60 degrees. So this angle of incidence here, this is 60 degrees, which is much greater than the critical angle. This means that the ray of light will undergo total internal reflection, and therefore it has to be reflected within the glass block, observing or obeying the law of reflection. So therefore we have to measure 60 degrees this side. So that is how you're supposed to score the 4 marks Part B of the question. The figure 5.2 is a full-scale diagram of a lens and an object. That means that this diagram is drawn into scale. The point marked F shows the position of the principal focus of the lens. Determine the focal length of the lens. So that this is a recall question. You need to know what to mean by the focal length. Focal length is the distance between the principal focus and the optical center of the lens. So our work is very easy here. Now that the diagram is to scale, we just need to do the measurement. And if you measure that, that will be 6.9 centimeter. That is 6.9 centimeter. The last part of this question, on the figure 5.2, draw two rays from the object to locate the image. Label the image I. On this side of the lens, the focal length is less, the length that we've been given is less than the focal length. So that means we can able to have another ray, and one of the ray is this. So a ray of light from the head of object which appears to diverge or come from the principal axis. So this ray of light, let's see. So the ray of light, so we use the head of the, let's use the pencil. So this ray of light appears to come from here and then passing through here. So this ray of light will be refracted by the lens such that it will be parallel to the principal axis. So just to confirm that it is parallel, let's measure that particular point. So that is 1.5. So we can measure 1.5 somewhere here. Okay. So we use this. There's a ray of light which passes through the optical center of the lens from the head. This ray of light is never deviated. So if you have a look at this particular side here, if the eye is somewhere here, then you can able to see clearly that these rays are diverging and they will never meet anywhere this side of the lens. That means they will appear to come from this side. So with this ray, this will appear to be from here on a straight. So just extend it or extrapolate. But of course it is not sort of real ray, so it will be dashed. Then also we extrapolate this. Wonderful. So the image will be, the head of the image will be at the point of intersection. So this is where the head of the image is. And this image, when drawn, remember it is formed by virtual rays, and therefore we will sketch as virtual, that is dashed lines. Wonderful. So this is our image I. Let's see. Our aim is just to draw and locate where the image is, and that is where it is. So figure 5.3 shows a simplified diagram of an eye with rays from a distant object and the path of the rays inside the eye of a person with a short sight. The diagram is there. Now, on the figure 5.4, draw an additional lens outside the eye to correct the short-sightedness and show the path of the rays inside the eye. Now, you can able to see here clearly, we have different types of lens. So we have, we have the concave lens and we have the convex lens. Now, this convex lens converges the ray of light, then this diverges the ray of light. So we don't want to use a convergent, because if you're using a convergent lens, it will even converge, it will make the rays to be converged even nearer the eye lens than the retina. That means we need a diverging lens to correct the short-sightedness as shown. So the rays of light at the concave lens, they get diverged. After diverged, then this convex lens converges the rays of the light at the retina. So this is the correction that is needed. Of course, you can draw a number of rays, but those two demonstrate what needs to happen.
Question number 6, part A. Sound waves have compressions and rarefactions. Explain what is meant by compression and rarefaction. Compression is a region of high pressure. So there is a region of high pressure where the particles are much closer than usual. So the particles are closer together. So when a sound wave is traveling, so when the wave is passing through air, the vibration of the particle is such that sometimes the particles, become very, very close to each other. That is now compression. Or the particles are further apart than usual, or than normal, than usual. So this is like a region of low pressure. Either is fine, so you can use pressure or just the particles enough. We can see light from the sun, but we cannot hear any sound from it. So if we cannot hear any sound, that means there is no vibration. So we know that sound wave require medium for transmission. So we know that in space, there is no particles to vibrate, while light does not require any medium for transmission. So light can travel, or you can just say light travels in vacuum. That is why we can able to see it. So in space where there is no medium, light still travel, while sound will need medium. During a thunderstorm, an observer sees the lightning almost immediately, but hears the sound of the thunder several seconds later. The thunder and lightning are produced at the same time. The sound of the thunder is heard 9.0 seconds after the light is seen. The speed of sound in air is discovered the distance from the thunderstorm to the observer. So we know that speed is given by distance divided by time. We are looking for distance. So distance is speed times time. That is 340 times 9 is equal to 3060, which is 3,100 meters. Okay. But D, in a lightning strike, there is a current of 3.0 times 10 power 4 amps for 48 milliseconds. Calculate the charge that flows. Now, charge is given by IT, that is current. So current is 3.0 times 10 power 4 times time, which is 48 milli, is a prefix, which means 10 power minus 3. So that is times minus 3 seconds. So we have 3 times 48, get 1.44. That is 1440 or 1400 coulombs. 1400 coulombs. We move to question number 7. Define potential difference. Define potential difference. Energy transferred per unit charge through a component. Through a component, or you can say that is work done per unit charge through a component is the same. So state the equation which defines electromotive force. So electromotive force, which is EMF. So EMF is given by work done per unit charge. Work done per unit charge, or energy transferred per unit charge. So the EMF of the battery is 9.0 volts. The battery is in a circuit. Calculate the work done by the battery when it moves a charge of 30 coulomb around a complete circuit. So that means that work done will be equal to the EMF E times the charge Q. That will be 9.0 volts times 30 coulomb, which is 270 joules. A circuit consists of a DC power supply, a lamp, and a thermistor. Draw a circuit diagram of these 3 components connected in series. So a DC power supply, so we don't know how many. So if you don't know, we can have 2 like that, or dash. We don't know how many cells are there. Then we have a lamp in series with a thermistor. This part must be parallel to the side. We connect to that bump. That's it. So they are testing if you know the symbol of a lamp, symbol of a DC power supply, and thermistor. Okay. Explain what happens in the circuit you have drawn in serum 1 when the temperature of the thermistor is increased. So when the temperature of the thermistor is increased, the resistance will decrease. Resistance of the thermistor decreases. So the resistance of the thermistor decreases. That means the total resistance of the circuit, also decrease. And what is the effect of this? More current flow. So what will we observe? The bulb lights brighter. The bulb lights brighter. Figure 8.1 shows a horizontal flat coil in a magnetic field. Okay, so this is coil. If I look at this coil is connected to a shell, meaning this is about a motor. This is about motor effect when there's a battery. The coil is connected to a cell. The coil rotates. Okay. Determine the direction of the movement of the side AB relative to the plane of the coil. Direction of the movement. So this one here, we have to apply the Flemmings left-hand rule. If this is the positive, it means the current for, let's consider on side AB. So side AB, consider your left finger. Sorry, consider your left hand. So the second finger is pointing the direction AB, while the first finger should point S. If you manage to do that, you will realize that side AB will be deflected downwards, and automatically this side will move up. So determine the direction. So AB will move downward, and that is according to the Flemmings left-hand rule. Okay. Explain how you determine the direction in A. I already explained. So current, so when you have the first finger, second finger, and the thumb mutually at right angle, then the first finger will point the direction of the magnetic field. So by applying Flemmings left hand rule, Flemmings left hand rule, what does it mean? It means that the first finger points the direction of the field. Second finger points the direction of the current. Direction of the current, that is from A to B, and therefore the thumb points the direction of the force. You're just explaining which is where the coil is being deflected. State and explain what happens to the coil as it reaches the vertical position. So the vertical position, at the vertical position, so remember, for it to move the vertical position, there was kind of flowing through it. Now when it reaches the top, if it moves forward, the changing direction of the current will be like in the same direction. There is no coil. So for this particular question here, for this diagram here, there is no split ring. So therefore, the coil will stop. Coil stops and tends to vibrate because there's no change of direction of current. So it tends to, move forward, backward, because there is no change of direction of the current. Part D, to operate as a motor, a split ring commutator and brushes are added to the part shown in the figure 8.1. Explain the effects of the split ring commutator and the brushes on the action of the motor. Now, just the same way as I've mentioned in part C. In part C, there's no split ring, or in the diagram. So the split ring commutator, what it does, it reverses reverses the direction of the current when the coil is at right angle with the magnetic field lines, so that it ensures that it moves continuously. But then the brushes just provide the contact. So the brushes provide the contact between the coil and the power supply. And overall, this ensures that the coil rotates continuously. So the split ring and the brush together. By doing this, so by the split ring reversing the direction of the current and the brush providing the contact between the coil and the power supply, it ensures that the coil rotates continuously in one direction. Number 9, a nuclear power station has a reactor where controlled nuclear fission of uranium-235 takes place. Explain what is meant by nuclear fission. Now, nuclear fission, we just know that is the splitting of a large nuclear into smaller nuclei, but then that will not give us 3 marks here. Nuclear fission here for uranium-235 is when uranium-235 absorbs a slow-moving neutron, to form a heavy nucleus of uranium-236, which splits into 2 nuclei. That is, if you want to be specific, barium and krypton, and is accompanied by release of energy. So the most important things here, we are looking at the neutrons, then the splitting of the nucleus, then that release of energy. Those are the main points for that particular question. Problem 2, state one advantage and one disadvantage of generating electrical power in nuclear power station compared with electrical generation with the wind turbines. So one of the advantage here is that if you look at in terms of pollution, generating electrical power in the nuclear power station does not cause air pollution. You have to be very categorical. If you just mention does not cause pollution, you might be wrong, because it causes visual pollution. So does not cause air pollution. And then one of the major disadvantage, there are several of them, but what we know is that nuclear power stations, the nuclear energy is not renewable. That means it is non-renewable. It's not renewable. There are also major dangers if there is any leak due to radiation that affects them. Now, part B of the question, deuterium is an isotope of hydrogen H with 1 proton and 1 neutron. Nuclear fission occurs when 2 nuclei of deuterium combine. An isotope of helium and a neutron are formed. So nuclear fission is literally speaking, is the opposite of nuclear fission. So nuclear fission is the splitting, while nuclear fission, from the word to fuse, is the joining together of light hydrogen. So if we have one proton and one neutron, that means the mass number of deuterium is 2. So we have H2 1 plus H2 1. This gives us helium, which is helium atom with one neutron. Neutron has that is 1 1 1 0. Sorry, neutron has no charge, so 1 0, and there is 3 2. So what we need to know is that the sum, so this mass number plus the mass number here should be equal to this and this. So that is this side is 4, mass number is 4. This side also mass number must be 4. Neutron has no charge, so that is 0 plus 2 should be equal to 1 plus 1, which is 2. So that is balanced. Okay, number 10, part A, the time taken for Mars to orbit the Sun is 690 Earth days. The average orbital radius of Mars is 2.28 times 10 power 8 kilometer. An Earth day is 24 hours. Calculate the average orbital speed of Mars in kilometers per second. So for this equation here, we assume that the orbit of Mars around the Sun is circular, and therefore we know that speed is given by distance over time. The distance here is the circumference, which is given by 2 pi r over the time taken. The time taken is the time for one revolution. So 2 pi times r, that is 2.28 times 10 power 8 kilometer. The time is 24. The time is 690 days. So 690 days, we convert it into hours by multiplying by 24. And because we need our answer in kilometer per second, so this 24, so the number of hours, we multiply with 3,600 to convert in, to give our answer in kilometer per second. So by using a calculator, calculating that should be 24 kilometers per second. So the shape of the orbits of the planet. So in real life, with the scientific discovery, the shape of the orbits of the planets is elliptical. Light from a distant galaxy is redshifted. Redshifted means that there is increase in wavelength, increase in the wavelength. So this increase in wavelength is due to the change of wavelength when the galaxy is moving faster, away from the Earth or away from us. That's the quantity that the redshift of galaxy is used to calculate. So this is from Hubble's law. We said that V is directly proportional to D. Sorry, these are the answer. So V is proportional to D, where V is the recession speed or velocity, which is the speed at which the galaxy is moving away from us, and the distance between where we are and the galaxies. So this quantity is the speed of the galaxy as they move away from us. So that is all.